Hi, I'm Alistair, and in this video I'm going to show you a new electronic puzzle. So what I've got here is I've got 4 toggle switches and a mag lock at the bottom. There's an Arduino on the back of the board, and there's also a mysterious blue button here, which I'll tell you about in a minute. So this is, on the face of it, a very simple puzzle. What the player has to do is turn these switches on to the correct on-off position, and when they do, the mag lock will release and fall on the floor. So at the moment, the solution is for all the switches to be on. So if I click that on, and then when I click this last one on, the mag lock falls off. Okay, now that's not a very interesting puzzle, and it's not very interesting for 2 reasons. The first of which is obviously the solution at the moment is just turn all the switches on. Not very interesting. And the second one you may be wondering is, well, why do I have an Arduino on the back of the board? Because to do a puzzle like this, you could just connect all these switches in series. When you flick the last switch on, you complete the circuit and allow current to flow or to break to the mag lock. And that's also where the blue button comes in. So what I'm actually doing is I'm reading each of these switch states separately and comparing them in code to a solution of ons and offs, which I'm expecting. When you press the blue button though, what it does is it will read the state of the switches at the moment and set that to be the solution. So let's say I want the solution to be on, off, on, off, for example. So if I set the puzzle to that state, then press the blue button, what it will do is store that pattern. Now let me put the switcher somewhere else and put the mag lock back on. There we go. So that's obviously not the right solution at the moment. If I set it back to on, which is what I had the first time round, that doesn't work either. What I now need to do is set on, off. Was it on, off, I think. On, off. There we go. And the mag lock falls off. So what this is a toggle switch puzzle that can be easily changed to any solution you want through code. And then this button here obviously wouldn't normally be accessible to the players. This would be inside the belly of the puzzle somewhere. But rather than have to change any code and upload it, or rather than have to rewire the switches or anything like that, all you do is you set the state of the puzzle to what you want the solution to be, so off, on, press the button, and then that becomes the solution. So off, on, now releases the mag lock with a funny noise. So let me just show you what is going on the back of the board, because obviously you can only see half of the puzzle at the moment. This is the exposed side. On the reverse of the board, so each of the switches at the top has 3 connectors. They're all wired to a 5-volt line, which is coming from an Arduino Nano at the bottom, and they're also all wired to ground at the bottom. And then, so they're the red and black wires. And then they each have their own individual signal wire, which are these yellow wires, and these are going into digital pins on the Arduino 2, 4, 6 and 8. I'm just using those pins because they're kind of lined up quite neatly with where the switches are, but you can use any digital inputs on the Arduino. And then on the reverse side here, I've got a 5-volt relay module. This is connected to 5-volt and ground, and it has a signal line coming in here, which is, it's actually plugged into the A1 pin. Just a reminder that all the pins on an Arduino, even the ones that are labelled as analog inputs, can be used as digital outputs as well. It's just that the ones that are analog inputs they're the only ones that can be used for analog inputs, whereas these can be used for digital inputs, but they can all be used for digital outputs. And then the mysterious blue switch here, this is wired also to ground, and that also comes into the A0 pin here. On the other side of the relay, I've got a 12-volt supply, which is broken by the relay itself. That comes round to power the mag lock. So when the relay is energized, it will make the normally open connection and the common connection connected together. That will energize the mag lock. And then when the relay is deactivated, the common connection will fall back to the normally closed position. And here's the layout as shown in Fritzing. So I've got my Arduino Nano here in the center, and I've got the 4 missile switches along the top. So the switches I got there's sort of lots of different sorts of toggle switches you can get. You can get single pole, dual pole, single throw, double throw, ones with LEDs, ones without, lots of different varieties. So the ones I've got are commonly described as missile switches, and they actually have like a cover that goes over the top, but I haven't put that on. And these are really nice actually. So they've got a built-in LED of different colours, and what you do is you have a 5-volt signal going to this pin here, and you have a ground going to the pin on the opposite side, and then the pin in between, that's going to be the one that is open or closed depending on the position of the switch. And the LED that's on the tip of the switch also comes on or off automatically based on the position of the switch. So if it's in the on position, the LED is on, and off, it's off. So these are all wired in series. They're sharing this 5-volt line goes through every missile switch, which comes into the 5-volt. If you can see that there, that's the 5-volt pin on the Nano. And the ground wire, again, they share all in series. This black wire, which comes in here. And each switch has its own digital pin, which are going into 2, 4, 6, and 8. But as I said, you can use any pin that's capable of doing a digital read for those. And then down the bottom here we have my mysterious blue switch. That is simply wired to ground on one pin, and I'm going to the A0 pin on the other. Again, can be any digital pin for that. And I've got a 5-volt relay here, which has got, again, a 5-volt and a ground input and a signal line, and that's going to A1. And on the opposite side of the relay, I've got my 12-volt input here, which is powering the maglock. Okay, so here's the Arduino code, and the key thing about this project, which I haven't shown in any other tutorial, is the fact that it makes use of the EEPROM library in the EEPROM on the Arduino. So EEPROM stands for Electronically Erasable Programmable Read-Only Memory. Now you're probably familiar with different sorts of memory that you might get in computers and processors. So you get RAM, which is generally erased every time the computer is turned off and back on again. And you'll get sort of different sorts of permanent storage, so SD cards and hard drives and things like that, which can persist data on and off. And that's basically what the EEPROM is like. It's like a tiny little hard drive on the Arduino. Now, depending on which model of Arduino you've got, you might have 512 bytes or a kilobyte, or I think 4 kilobytes in the megas of storage space. So it's not very much. It's not enough to hold anything like the size of a picture or video or music file or anything like that. But if what you want to do is store some configuration data that is in the form of, a couple of bytes of Boolean values or integer values or something like that, it's absolutely perfect. And that's what we're going to be using in this project to store the solution, so that each time you turn the Arduino off and on again, it will remember the last saved solution that you set. So that's what. So the first thing we're going to do is we're going to include the library that lets us use those functions on the Arduino. I've got some constants, so in this example I'm using 4 toggle switches, but you can use as many as you want so long as you've got enough digital pins to account for them. And these are the digital pins that I've got them wired into. Here's the pin that my save button is wired to on one side and ground on the other, and that's the pin that the relay goes to. Now, this is another slightly funny thing. When you write data to EEPROM, I always find it's a good idea to kind of make sure that your saved data is valid and successful, and particularly when you're reading it back again, you want to make sure that you know that the data is good before you load it in. So what I've defined there is just a really simple, it's a single byte value. So I'm using 121, but you can use any value you want just between 0 and 255, so it gets stored in a single byte. And I'm going to use that just as a kind of a check value. When I've finished writing data onto the EEPROM of the Arduino, I'm going to write this value back again. And if that value appears, when I load it, I'm going to say, okay, I know this data is good because it's had the right signature byte written to it. If the data was corrupt in some way, or if the save wasn't successful, then that value wouldn't get written at the end. So I'm using that just as a really simple way of knowing whether the data is good or not to load up. I've got some global variables which are used throughout the project. So I've got an array of Boolean values that is got the number of elements in it of the number of switches. So I've got one Boolean value for each switch, and that just says the last known state, whether it was on or off or true or false. This keeps track of the state of the overall puzzle. So is the puzzle just starting up at the moment? Is it active, as in it's running but the switches are not in the correct solution position yet, or are the switches in the correct solution? And obviously we'll start off with the puzzle in the initializing state. And this is the value, this is the array that's actually going to store the desired solution. So where do I want the switches all to be? So I'm initializing that with them all just being true, so all the switches on. But this is the value that's going to get overwritten when we load the data in from the EEPROM. So, speaking of the EEPROM, the next two functions deal with saving and loading data to it. So it's actually really simple to use this EEPROM. So there's a couple of functions we'll use which effectively just come down to reads and writes. So in the very first byte of the EEPROM, that's where I'm going to store that signature to say whether the data is any good or not. But the first thing I'm going to do when I save new data is to actually erase any signature was there. So always the first stage in the process is to kind of invalidate the data that was there, and then we'll check it back again. So that's what this does. This says it's going to write a value into the 0th address in the EEPROM. So the very first value we're just going to erase. So we're going to write a 0 byte there. And then what we're going to do is we're going to loop over all the switches. We're going to set the desired solution to be whatever the last switch state is. So we're going to read their current value and set the solution to that value. And then we're going to write that onto successive bytes of the EEPROM, starting at i+1, not I, because remember that the 0th value in EEPROM, the very beginning of the EEPROM, is going to be my signature file. I'm actually going to write starting at the second byte in. So that's going to have the address of i+1. So that's what that does there. If this is all successful, all those values have been written, the code's still running, then what I'm going to do is I'm going to write back the EEPROM signature back into the beginning of the EEPROM data set. So that 0th byte I'm going to replace with the EEPROM signature again. And then finally I'm just going to dump something out to the serial monitor if we've got one connected, just to let it know that it's happened. So that's all about how the pattern is saved. And then it's got a matching function which is concerned with loading the data again. So it's basically sort of the same in reverse, really. So the first thing it does is it checks the value of the first byte in the EEPROM, and it checks whether that is equal to the EEPROM signature we decide. So that 121 value, or whatever value you want to assign just to this puzzle to say this is valid data. If that matches, then what we're going to do is, like I say, it's kind of the inverse of what we were doing before. When we were saving, what we were doing is writing to the i+1th address of EEPROM from the last switch state. And what we're going to do now is we're going to be reading from the i+1th address of the EEPROM memory, and we're going to be overwriting the solution with that value instead. If that's successful, then we'll just update to the serial monitor and say the solution was loaded, and if it's not, we'll put a message up saying that we didn't find this matching signature here, so the EEPROM data wasn't valid and it wasn't loaded. Okay, I've got one more, or a couple more helper functions actually. So this is very simple, you might have seen in some of my other puzzles. So this just reads the state of the switches. So it's going to loop over all the switches. We're going to use a digital read here. So this is just going to give us a high or a low value of each of the pins to which the switches are assigned. And then if that's different from what the last known value was for that switch, we'll just say that it's changed, and we'll just put a little debug message up to say what it's changed to, and we'll update the value that we knew for that switch. So this is just debugging information. You don't need this in the final puzzle, but it's just to check that everything's working when you're testing it and developing it. So if it's different from what we thought the value for this switch was, we'll just update the stored value. That's all that does. And then we've got a function here that tests whether the puzzle is solved. So again, what we're doing here is we're looping over every switch. So it's the same kind of idea in many of these functions. We've got a series of inputs, and however many inputs we've defined, that was the number of switches, we just loop over all of them. This time, rather than saying whether the current value is different from the switch state, what we're going to say is if the state of this switch. So let me go back over that. Sorry. So we're saying. So what we're going to do is we're going to assume the puzzle has been solved. Okay, when we test each time, we'll assume it's been solved. Then what we do is we loop over all the switches, and if any of them is different from the solution value we're expecting, that's what the exclamation mark equals means, then the puzzle has not been solved. Now, that kind of seems like it's set up backwards, but this is actually quite a common way of setting these kind of tests. If we assumed that the puzzle had not been solved, what we'd have to do is go through each of the switches and make sure that every single one of them was correct. But if we assume that the puzzle was solved to start with and instead test for the opposite to make sure whether any of them is wrong, all we have to do is know that one of them is wrong, because as soon as any one switch is wrong, we know that the entire solution must be incorrect. So that's why it's kind of set up in this reverse way, which might seem a little bit strange, but it's actually kind of an easier way to write the logic of the code. And at the end of that function, we'll just we'll return that solved value and say, okay, well, did we get all the way through this loop without any of the switches failing the test? And if we did, then the puzzle's been solved. Okay, so here's the setup function. This is what's run when the program first starts running. Once again, we loop through all the switches. So this is getting rather familiar by now. And we'll set the switch pins as inputs. We'll set the save pin as an input pull-up, because it's going to ground on the other side. And we'll set the relay pin as an output. Now, the reason why the switch pins are inputs and not input pull-ups, so remember that they've actually got a 5-volt connection, a ground connection, and a signal wire connection. And what happens is they've effectively they've got a built-in pull down in them. So when this switch is off, the signal line is connected to ground, and when it's on, it's connected to high. So we don't need to use the pull-up resistors that's on the Arduino, and we don't need to add any additional resistors because it's kind of built into the body of the switch. The save pin, however, that was just a momentary push button, and if we defined that as an input, then when the button wasn't being pressed, it wasn't connected to anything. It's not grounded, but it's not connected to a high signal either. So the input would kind of waver between them. So that one we have to define as an input pull-up. And the relay pin is obviously an output, because that's where we're going to send a signal to activate or deactivate the relay. We'll initialize the serial connection, and then the first thing we'll do when we're loading up is to load the pattern that is saved on the EEPROM. So that calls that load pattern function that we looked at up here. So that happens every time the Arduino starts up. It reads the EEPROM and sees whether there's a valid solution saved, and if so, it loads it up. And then finally, at the end of the setup function, we'll go, okay, we've completed all the setup actions. Let's set the puzzle state to active. And then this is the main loop of the program. So on every loop, on every step through while the program is running, this continuously just runs over and over. We'll read the state of the current set of the switches, and that calls the function that we saw defined earlier. We'll check whether the save button's being pressed. Now remember, this is connected to ground, so digital read save pin is low, means that the button is being pressed. And then we'll just put a really simple, those momentary push button switches, when you press them, you can sometimes get a bit of bouncing, which is where you kind of get a high-low, high-low, high-low signal just as they're being depressed. So to prevent that, what we'll do is we'll just wait for 1/10 of a second until the button is released. So this line here will kind of just stay running in a loop there while the button's being pressed, and then when it's released we'll save the pattern to the EEPROM. And then we'll say, has the puzzle been solved? That calls the function that we defined earlier. If the state of the puzzle is currently active but it's now solved, we'll just dump a message out to say the puzzle has been solved, and what we'll do is we'll deactivate the relay, which is going to release the maglock, and we'll update the puzzle state. Alternatively, if the state that we last knew the puzzle to be in was solved, but the puzzle is no longer solved, so at least one of the switches is in the wrong position, we'll say the puzzle has become unsolved, and we'll set the relay back to high, which is going to lock the maglock again, and we'll update the puzzle state to active. So there you go, that is my toggle switch puzzle that is easily set to a different solution puzzle without requiring any rewiring or any re-uploading of code or anything like that. It just uses the EEPROM on the Arduino to store the solution, and that's restored each time the Arduino is reset. I hope you found that helpful, and if you've got any questions or comments, please let me know below. Thanks very much for watching.